It's time to talk about irrotational motion. So, irrotational motion. If you remember that video, one of the videos we showed in the Hunter Rouse movies, they showed this flow over some airfoil body, and close to the airfoil, of course, there's high rotation, okay, going on. However, away from that, the streamlines are kind of nice and smooth, and in the experiment, what they did, if you remember, they put in a little cross like this, same length, and they showed that that cross just sort of translates with the flow. It doesn't rotate at all. And so this entire region consists of what's called irrotational flow. Now specifically, irrotational motion is derived by assuming that omega, or the vorticity vector, is equal to 0. And what that means is that omega equal curl u is equal to 0. It just means that there is no rotation in the flow. And one of the ways to think about rotationality is to consider the following two types of vortices. The first one is called the irrotational vortex. Irrotational vortex. And in such a vortex, there's a center. There are these concentric streamlines with only a tangential velocity component, u theta, and this vortex is given by ur equals 0, and u theta is equal to some constant over r. And if you create a vortex like this, so essentially the center velocity is the largest, so this is kind of what happens in a drain, and then as you get away, the tangential velocity goes to 0 as r approaches infinity. So this would be your r. And what happens here is if you take this oriented cross, two sticks of the same length, as they move around, they will retain their orientation. Okay, they will retain their orientation. It's really cool. Now, to prove that this flow is irrotational, all we have to show is that omega, the only non-zero component of vorticity, which is omega z, that's given by 1 over r d by dr r u theta minus dur by dz, and that's equal to, now this guy is 0 because ur is 0, so that gives us 1 over r times d by dr of r. What is u theta? K over r, and so r and r cancel out, and k is a constant, so therefore indeed vorticity is equal to 0. Now this is called the irrotational vortex. Contrast that to the forced vortex, which is given by a similar configuration, okay, but that vortex is given by the following velocity profile. Again, this is r. ur is equal to 0, however u theta is equal to k times r. So in other words, the tangential velocity increases with distance from the center, similar to somewhat like a tank rotating on the outside. Now, in this configuration, you can show that if you put cross like this, it is going to start rotating. Etc. and so on. Now the vorticity in this case is omega z is equal 1 over r d by dr of r u theta of r times k times r. So that gives us k over r times 2r, or in other words 2k. Now this constant is essentially the rate of rotation of the vortex. Now this gives you an idea on kind of how to think about vorticity and what vorticity does to a fluid flow. Now let's go back to irrotational flow. In irrotational flow, we said that, let me use a marker, we said that omega was equal to curl u was equal to 0. Now, when is this true? Remember, when we always said that curl grad p is equal to 0, because the curl of the gradient of a scalar is always 0, then this necessarily implies that u must be of the form grad phi. That is a very important result, because we went from 3 unknowns, u, v, w, to a single scalar valued function phi of x, y, and z. And u is given by grad phi, so u is equal d phi by dx in Cartesian coordinates, v is equal to d phi by dy, and w is equal to d phi by dz. This is pretty powerful. Now, in that case, if that's the case, we can now take this idea that u is equal to grad phi and apply, so apply u equal grad phi to Navier-Stokes equations. And we will be doing this for constant density flows. The same can be done for compressible flows, but it's a little bit more complicated. The fun and easy results are with the constant density case. So we start with continuity. Div u equal to 0 implies that if u is grad phi, it's div grad phi is equal to del squared phi equal to 0. Okay. And for the Navier-Stokes equations, we had du by dt plus u dot nabla u is equal to minus 1 over rho grad p plus nu del squared u plus g. Okay. Now substitute grad phi. We get d grad phi by dt. Okay, great. Now, what about this term? This guy. Remember, we can write u dot nabla u as 1 over 2 nabla u squared. So u dot u minus u cross omega. But because omega is equal 0, so this means that the convective term is simply 1 over 2 grad u squared. So we get plus 1 over 2 grad. Now what is u is grad phi, so we get grad of grad phi squared equals minus 1 over rho grad p. We can't do anything about the pressure. Now this is an interesting term here, del squared of grad phi. What is del squared grad phi? Well, think of it this way. I want to write d2 by dx squared d phi by dx. That's equal to d by dx of d2 phi by dx squared, right? So therefore, del squared grad phi is really just equal to grad of del squared phi. Why am I writing it this way? Because I know that del squared phi is equal to 0 by virtue of continuity. So this term is really just equal to 0, the whole thing, because this is equal grad del squared phi, okay, plus g. Now I need to make a very important note over here, that irrotational flows, there's nothing in this derivation that tells us that irrotational flows are inviscid. In fact, go back to the example from the Hunter-Rouse experiments. That's the flow that they showed. I think that was glycerin. That's a highly viscous fluid. And yet they were able to show that there are regions in the flow where the flow is irrotational. Viscosity is there, the fluid is viscous, it's just that the net viscous forces are zero. They cancel out. But you can calculate a shear stress at one point. You can calculate any quantity that has viscosity in it, except that you will find that the net viscous forces or the net diffusive flux of momentum, remember this term comes from diff tau, and that's a net diffusive flux of momentum through the different directions, okay? And that net diffusion is zero for irrotational flows. And so saying that irrotational flows are inviscid, that's technically incorrect. So irrotational flows does not imply inviscid. Okay? Now, in practice, and the reason that people get confused about this is, is that typically a viscous fluid is always associated with rotation because vorticity produces the no-slip, because viscosity produces the no-slip condition, and when you have a no-slip, that forces the velocity to go to zero near a boundary, so close to a boundary, the velocity is going to go to zero, but then everywhere else it's something different, and that produces rotation. And indeed, we're not claiming that we want to use an irrotational flow assumption near a solid boundary. That's completely unacceptable. You can't do that. But for regions away from solid boundaries, or you can very fairly use the irrotational flow approximation. And in the historical development, as we will see when we discuss the boundary layer theory, you can split the region of a flow close to a solid body. You can assume that the flow is viscous over here. We're going to call this the boundary layer. And away from the flow, you're going to have irrotational flow. So omega is equal to zero. Okay. So now that's cleared out, we can look again at these two equations. We have the continuity giving us del squared phi equals 0, and the momentum equations turning out into this kind of interesting set of equations, but we still have phi and p over here. However, from continuity, if we can solve for phi from continuity, that's enough to give us the complete specification of the flow. And then we can take phi and plug it in here to compute the pressure. And that's a very interesting way of solving this problem, and that's how typically it is done. The continuity equation is enough to allow us to compute, with given boundary conditions, to compute the velocity potential phi. By the way, phi is called the velocity potential. Now, compared to the previous formulation where we dealt with continuity and full Navier-Stokes, you cannot solve using the continuity equation for the velocity field. You cannot use the continuity equation to solve for the velocity field because you have three velocity components, and the continuity alone is not enough for that. And therefore, you can't just use the continuity equation in the previous configuration. So the procedure over here will be to do the following: use continuity, del squared phi equals 0 with boundary conditions to solve for phi, substitute phi into momentum equations to compute the pressure. As simple as that. Now, for boundary conditions of for the del squared phi equals 0, del squared phi equals 0 is called Laplace's equation. Laplace's equation. And from math theory, you can show that the only boundary conditions for this equation are nu of the Newman type. So they're normal boundary conditions to the boundary. Now, from a physical intuition, phi is related to the velocity field. And for the velocity field, we have two types of boundary conditions. We could apply no slip, which means u dot t equals 0, where t is the tangential vector, and impermeability, assuming a stationary wall, then u dot n is equal to 0. So if you have a surface like this, then this would be the tangential unit vector, and this would be the normal unit vector. Okay. Now, if you think about impermeability, that's really just a statement of mass conservation at the boundary. Mass conservation. It's related to mass conservation. And this one is just another effect thanks to viscosity. Now, you can argue that, well, one, we don't have enough constants when we integrate this equation to apply both boundary conditions. We can apply only one or the other. And they will be inconsistent. You cannot apply both because they're going to give you two different answers. They're not going to give you a unique solution. However, if you apply this one, you're not going to get mass conservation. So we'd rather get away with mass conservation, and that will give us this equation. Okay, so this takes precedence over the no-slip condition, and that's why potential flows have slip in them, and that's why we think typically that they don't apply to viscous flows. They just don't apply to viscous flows near boundaries, near solid boundaries. So when that's out of the way, with that being out of the way, now we can look at one more thing. We have to look at one more thing before we start finding solutions for del squared phi. We have to look at how we can integrate the momentum equations in this case. So we're going to look at the momentum equations again, du by dt plus u dot grad u is equal minus 1 over rho grad p plus nu del squared u plus g. Okay, for omega equal 0, this turns into du by dt plus 1 over 2 grad u squared equal minus 1 over rho grad p. We just showed that del squared u is 0 plus g. Now, if you look at this equation, we have gradient over here. If we can put everything under a gradient, so in other words, if I can write this equation as grad q equals 0, then we can claim that q is equal to a constant. Think about the Bernoulli equation that we derived in the past. Can we do this? Yes, absolutely. First, starting with this term, we can either assume that this, if we assume this guy is 0, in other words, unsteady flow, then this term disappears. But for, in other words, steady flow, then this term disappears. But for unsteady flow, we have del grad phi by del t, right, plus grad 1 over 2 u squared, plus 1 over rho, or plus grad p over rho. And this guy, remember that we can write this guy, g is equal to grad minus gz, where g is 9.81 gravitational constant. And so we get plus grad gz is equal to 0. Now everything is in grad form, and therefore we can say that d phi by dt plus 1 over 2 u squared plus p over rho plus gz is equal to a constant. Now, what is this equation? That is the Bernoulli equation. Unsteady Bernoulli equation. Bernoulli equation. However, what's the difference between this case for irrotational flow and the previous case where we said the Bernoulli equation applies only along a streamline? It has to do with this particular term. Now, this term was grad 1 over 2 u squared minus u cross omega. when we set out to write everything in gradient form, we couldn't get rid of this term. So we said, take this term along a streamline, that will make this term, u cross omega dot ds, that will make this term equal to 0. And therefore, we were able to integrate the Bernoulli, to do the Bernoulli equation along a streamline. But that will give us a different constant for each streamline. However, in the case of irrotational flow, this term is 0 everywhere in the flow. There is no specific condition to set this flow, to set a different constant or to have a different constant for different streamlines. This thing is valid across the entire flow field, and so therefore this constant is the same everywhere. And we did allude to this in the past. I'm just reminding you of the power of the potential flow over here. Now, this d phi by dt term is a little bit interesting. We'll take a tangent, a shortcut later on to discuss what we can do with that term. But for now, this gives you kind of the first insight into potential flow.